Hello, my name is Denis Gladkih, and in this video we're going to talk about containers. We will try to answer on the questions: what is container, what is orchestration, and how the container is different from virtual machine. Let's start from the beginning. You have two services that you need to deploy in production. How you used to do that? You can deploy them on the same virtual machine if you have capacity to do so. What if they have a library that they both depend on? So you can deploy this library on this virtual machine like OpenSSL library, and each service will have ability to use this library. But what if these services require different versions of this library one? So you can deploy this library within the service. As an example, it can be if this is a Java applications, you can deploy this library inside of the jar file. If this is Python applications, you can deploy these libraries inside of virtual environment. If this is OpenSSL library, you can just override the library path for loading the libraries. But what if these two services write in the same location? For example, in temporary folder file service DB. In Linux, we can use chroot to change the root of every service. We can use chroot to change the root for the main process that's running our service. So every service, when it will try to write a temporary folder, it will have its own temporary folder. What if services bind to the same port 8080? How to solve that problem? Well, you can create virtual Ethernet interfaces for every service and let the services bind to these virtual Ethernet interfaces. Later, you will need to figure out how to route the traffic from the real Ethernet interface to these virtual Ethernet interfaces. What if one service uses a lot of CPU and memory and that actually causes issues for other service? Well, you can use cgroup to limit how much CPU this service can use and how much memory it can use. For example, systemd allows you to specify the cgroup's capabilities and limit the resources. A lot of tools and systems we mentioned existed in Linux and Unix world for a while. I just want to mention that in 2007, this is where cgroups were merged in Linux kernel, and in 2008, LXC, the first kind of tooling for using the cgroups, were merged as well. And in Docker introduced their way of working with the cgroups and namespace in 2013. Let's take a look again on our example. Let's think about what we actually need to make that work. So we have a service, we have chroot, we have virtual Ethernet interface, we have the libraries dependencies inside of chroot, and we have cgroup that limits CPU and memory for the service. So first, we have the content of file system under chroot, which contains our service, all the libraries and dependencies the service depends on. Think about this. This is actually can be some jar file that contains all of that together. Secondary is we need instructions to tell which process is actually responsible for running our service. And third, we need the system which will allow us to create this virtual Ethernet interfaces, start our service, our process, and limit the resources, including CPU and memory. So the third thing we mentioned is the content of file system. This is actually the image. This is what you heard, that this is a container image or Docker image. Image contains information about, it actually contains your service, all the dependencies that your service need to run. Secondary is Docker run defines how you want to run your image. Also, some of the instructions can be embedded in the image from the Docker file, and we will talk about that later. And third thing is, this is actually the Docker engine, the container runtime that helps us to take this image, using the instructions, start to create the virtual Ethernet interfaces, limit the resources with cgroups, and start the process that we defined with our instructions from the image. At this point, you can say, hey, I could do all of that with virtual machines. I can limit the resources, I can just deploy the package, I can even deploy the image with the virtual machine. But let's think about that. How long it actually takes to boot a virtual machine? With the stripped Linux kernel, with the stripped Linux version, maybe it can take like 10, 20 seconds to run. But how long it actually takes to run the new process? How long it takes to start the process? Around like a few seconds, right? Even less than that. It depends on like what kind of process we are talking about. Another problem is when you're working with a private cloud, you can actually define what kind of CPU you want to use, how much memory, and what kind of disk. It should be SSD or hard drive, should be fast disk, should be large disk or like small one. But in public cloud, you're limited with the choices given to you. And so a lot of times you can find, okay, this type of VM, for example, has enough CPU, but it has really slow disk, so I cannot use it in my workload. Another VM might have the disk that gives you enough speed, but at the same time, maybe it has too much CPU, so you will overpay for this VM. Also, I want to mention that kernel actually takes some space as well, meaning like it actually takes some resources, memory, and CPU as well. So if you run, for example, thousands of VMs, each has only one service, so you can end up paying a lot for just running the kernels on your inside of virtual machines. Now let's take a look on the Docker file. So as we mentioned, Docker file helps us to build images. An image is something that contains your service, all dependencies that your service needs to run. So in the Docker file, what we define is the base image. In this example, it's Ubuntu, which contains it doesn't contain the kernel because we don't need the kernel because the container will run on the real Linux environment using the host kernel. But choosing Ubuntu let us to choose, for example, use package manager, use all the base libraries from Ubuntu distribution, including like libc and everything else that Ubuntu provides in their base image. After that, we can copy our service in this case, for example, it can be binary up1 and copy it to the inside of the image. And third one is actually just an instructions. It puts inside of the image instruction that if you're not going to specify the command to run this image, by default, the command up1 should be used to run this image, to run the process inside of this image. After this, we can build this image, and that will actually produce the image that later we can run and create the container from this image. Every image can be tagged with the name and the version as well. Later we can actually run this image with a docker run command. We can also specify additional instructions, like in this example we specify that we want to publish port 8000, and by that we means that if the service inside of this image exposes port 8000, we'll be able to access to that, and Docker will provide some random port that we can use to actually get access to the service. And important thing here, we haven't specified the command that we actually want to run inside of the image, inside of this container. And because we specified in the Docker file, this command will be used. So why containers? First of all, it's consistent everywhere. Because you package all the dependencies in your service inside of the image, you know when you will try to run it again and again and again, it will be exactly the same service with exactly the same set of dependencies. Secondary, it allows you to run anywhere. This means that a lot of cloud providers provide you capabilities to run the images within the Linux systems, and it doesn't really matter what kind of Linux distributions you use as a host operation system. It can be you can build your images in Ubuntu using Ubuntu base image, but at the same time you can easily run this on CentOS. And again, because all the dependencies for your package will be inside of this image, you will not depend on libraries, for example, in CentOS and the host operation system. It gives you isolation, meaning that you have isolation for CPU, memory, process namespaces, and at the same time, application will not be able to disrupt each other if you will not allow them to do so. It really has the small footprint on the disk because the images can be really tiny. It only has only the dependencies you specified that you want to use in this image. And because of virtual machines, usually we're dealing with the image sizes like several hundreds of megabytes. You can definitely grow your container images to the same size, but usually we are dealing with much smaller size of the images. And that provides you low overhead as well to run this. Let's summarize some of the terms. What's actually Docker? We talk about containers, we talk about images. You probably heard that, about the Docker, but what is actually Docker? First of all, Docker Incorporated is the company behind development of Docker. And Docker software is the containers runtime, orchestrators, and much more. It has two versions, Enterprise Edition and Community Edition. Community Edition is free, Enterprise Editions you get with the Enterprise subscription. Moby is the open source framework for building container runtime. So Docker software actually built from Moby, and Moby is a framework that helps you to build a container runtime. And Docker is the software that can be used out of the box. You can download it for your Mac or Windows and start using Docker right away. Containerd is the container runtime used by Moby. And so the difference between Moby and Containerd is just a runtime that will allow you to run the image as the container. Moby is the framework that helps you, for example, build images, specify different ways to write in logs on the disk, or maybe some other external systems, and provides you capabilities to use the other plugins to run with the containers, provide you capabilities to moving images between the different VMs and so on. And you might be heard also about the Docker Compose. This is a tool for defining and running multiple containers within Docker applications, within the Docker engine. So as an example, you can run your containers with Docker run command and maybe write make files or bash scripts to do that. But when you, for example, your application constitutes for more than one container, you want them to run together, you want to specify some dependency, maybe map volumes between each other, maybe create some network for them. So Docker Compose allows you to package everything in one YAML file, and using Docker Compose you can run everything together. Docker Swarm is an orchestrator provided by Docker's software, right? And we're going to talk what orchestrator is later, but it's just good to know that Docker Swarm exists. Docker Universal Control Plane is the enterprise-grade cluster management solution from Docker that built, at first it was built on Docker Swarm and provided with the Docker Enterprise Edition. And now they actually allows you to run Kubernetes workloads as well within the Docker UCP. Okay, we mentioned orchestration. So what is orchestration? Let's say you have now multiple services that you want to deploy with the containers. You have several virtual machines. How you usually deploy the services on these VMs? So one way of doing this, you can just name the VMs. For example, you can name one VM frontend 1 and another VM of backend 1. And so you know that all of the services that represent our front end should go there, and all the services represent our backend go there. By front end, I mean like services that actually helps to run our front end. What might happen later, because these VMs have some capacities left, right? You can end up running something else with these VMs because you found that, hey, I have these VMs and I see that maybe half of the CPU only used on VM1. Maybe I can squeeze a few more services here, maybe some infrastructure services. And on backend, maybe I can start running some cron jobs unrelated to my backend services, but because I have the capacity, I can do that. So it can comparing like if you have a lot of VMs, it can get messy. Also, other questions you want probably to find answers to is how, for example, we route the traffic from service one to database, how we know where the service one is, and how we route the traffic from external, from the load balancers to the service one. How we actually replace the virtual machine, how we scale the number of virtual machines, how we scale the number of running services, and we'll be able to run the traffic from load balancer to these services, how we actually push the images on that on these VMs. So that's actually what orchestrator will help us to do. Instead of talking to VMs directly, let's, for example, we'll have some service outside of our VMs or maybe running on the VMs that will help to work with these VMs as with just one instance, as just one service, as a one kind of like cloud provider. And instead of talking to VMs, we can tell to orchestrator that, hey, we want to actually run 3 instances on service 1, and we don't really care, for example, on which VMs it's going to run. Just make sure that it will run on VMs that have the capacity to do that. So that's basically what orchestrator is. It helps you to manage multiple VMs and run your workloads on these VMs and help to schedule them on them. If you will take a look on the Kubernetes as the example of orchestrator, you probably will find that there's a mention of master nodes and worker nodes. So worker nodes is basically the nodes where you just run your own workloads. Master nodes is services that helps Kubernetes to run. That includes control plane, including the database where we store the state, API server to where we actually talk, which from the CLI or some other services, and ask Kubernetes to run the workloads. So on Worker, we can use Docker as a container runtime. There's also some other container runtimes available like Creo or Containerd, for example. And Kubelet is a part of Kubernetes that can talk to the control plane and try to find what kind of images I need to run on this specific node. So Kubelet is running one per worker node and communication with the control plane and trying to figure out what kind of services it needs to run, and talking to the create the container runtime and running these services inside of the containers. On master node, we have a lot of services that includes again like Kubelet and Creo as well, because some of these services we deploy inside of Kubernetes environment as well. So we also have etcd is the database that stores the state and all the necessary information to run the Kubernetes. We have a scheduler that actually tells it figure out what kind of services this Kubernetes cluster needs to run and put this schedule this service on specific nodes. We have API server is the kind of front end for us. It's something we talk from CLI tools and ask API server to actually run some workloads and ask for the state and so on. And controller is something that helps us to create pods from the workloads we ask to do. So we'll take a look at some example later. Let's take a look on actually on scheme how all of that works. So the user can ask Kubernetes or this orchestrator to create the pod. And the pod, I know, is something new. It's a new term, but think about this as just one container. So we ask API server to create the container, and API server will write to etcd to the database the state that the user asks us to run the container. So API server also used by the scheduler. Scheduler actually watches for if there's some new pods created in the within the Kubernetes clusters. I mean, like somebody wants the new pods to be scheduled to run. And so the scheduler watches for this information, and after this, it will try to figure out based on the capacity of the nodes and what kind of other workloads these nodes already run. It will bind this pod to specific node, and all this information will go back to etcd. Kubernetes on every worker node and master nodes actually also watches for new pods bind to this specific node, and it will find that okay, there's new pod was scheduled to be run on me on my on the node where this Kubernetes is running. It will talk to the container runtime. This example can be Docker, and run this container. After this, it will update the state again using API server and write the state to etcd. And so now we actually have working container, and orchestrator did the job to actually run this container on one of the VMs. So what is pod? We mentioned that pod, you can think about pod as just one container. So pod in the sense of Kubernetes allows you to run multiple actually containers, multiple processes that will share the same network interface, and they can share the same volumes. As an example, it can be something that always need to run these two services together because they cannot exist without each other. And they will be able actually to talk on the local network interface to each other. They don't need to define external services, and you can schedule them all together, and they always will be scheduled together. And the pod will be successfully run only if the both containers will run. So let's define what is Kubernetes. Kubernetes is an open source container orchestration system. Similar to Linux kernel, very rarely you actually need to go and compile your Linux kernel. You usually get your Linux from the one of the Linux distributions like Ubuntu, CentOS, CoreOS, and Red Hat, and a lot of others. Similar to that, in Kubernetes, you can actually get your Kubernetes clusters from public cloud providers like Azure AKS, AWS EKS, Google Cloud provides Kubernetes versions as well, Kubernetes services as well. You can install your Kubernetes on-prem with Pivotal, PKS, and a lot of other examples. At the same time, you can actually go and use the tooling available in open source version of Kubernetes, like kubadmin, and build your own Kubernetes clusters. The difference between kind of public offering and some other offering depends on how much you will need to spend time to actually manage your Kubernetes clusters. In some cases, you don't have access to the master nodes. It will manage by the Kubernetes provider. In some cases, you will have to manage master nodes, and you will need to monitor them as well. Cloud Native Computer Foundation is the open source foundation to advanced development of cloud native application and services, and Kubernetes is the one of the projects within this CNCF. There's a lot of other open source projects, including Prometheus, FluentD, and a lot of others. OpenShift is the one of the Kubernetes providers as well from Red Hat. It's first of all, it's actually open source container application platform built by Red Hat, and it's based on the Kubernetes. But it also has OKD distribution. This is the distribution provided for free. It's open source, and there is also Red Hat OpenShift. This is the enterprise distribution of OpenShift that you can install on your Red Hat VMs and run there. Thank you for watching. I hope this was helpful. I hope you learned what is container, what is orchestration, how the container is different from VMs. I will definitely continue to making more videos, and in the following videos we will see how you can run your Kubernetes environments, how you can try Kubernetes on your local laptops. We'll learn different workloads that you can run on the Kubernetes environments. So thank you for watching again.